So I'm going to talk about simulation here, and even though it's not always perfect to talk about easy simulations, but how to make good benefit from simulation, I think is the main message I'm getting at here. Even though it's not always easy, but still a very useful simulation. So the idea here is if we would have a robust nonlinear simulation tool that can manage contact, it can manage large deformation, it can be able to use advanced material models, and that can be, for example, be able to take into consideration advanced joining techniques. We think that really would actually help us to design and produce better products in that we can, before we go to production, we can simulate the product performance in its real environment, which oftentimes also mean that we need to involve various kinds of multiphysics aspects of the product performance. So I come from Dassault Systèmes, and I am affiliated with the SIMULIA brand of Dassault Systèmes. And the purpose of Dassault Systèmes is to make realistic simulation an integral business practice. And ever since Dassault acquired Abaqus in 2005, this has been a key target of digital product development. Ultimately, with the target, of course, to significantly reduce physical testing in order to save time, money, and to improve quality. What we see on screen here are a couple of examples where we compare simulation results with actual physical testing. In that, of course, building the confidence that the simulations are indeed truly predictive and can be used to beforehand predict product performance and behaviors, rather than waiting for prototypes to demonstrate that. As that, SIMULIA is not a product and obviously not a company, so it's a brand of Dassault Systèmes, and as a brand we're populated by analysis products, or simulation products, if you will. The contents of the SIMULIA brand is constantly growing. I will, for this seminar, mostly focus on the products we have that are most pertinent to structural simulations. So that will be the Abaqus product portfolio. And I will also briefly touch on EyeSight and Tosca for optimization aspects, and FE-Safe for durability and fatigue assessment. So Dassault, which develops this software, is a purpose-driven, very large company, more than 20,000 passionate people around the world, with around 70 R&D labs around the world, and probably today more than 300,000 customers across the globe using our products. So with that, we will go directly to the topic of the talk today, which will focus mostly on Abaqus. So Abaqus consists of fundamentally three parts. We have the solver products, Abaqus Standard and Abaqus Explicit, which are the piece of software which actually do the structural simulations. They are based on the finite element technology. There's a front end to it, Abaqus CE, which stands for Complete Abaqus Environment, which is the graphical user interface that many of our customers use to interact with the solver products. I mentioned in my introduction that we really looking to have one simulation tool that will be able to simulate product performance in various conditions. And this is really true to our offering. In a normal sort of description of simulation activities, if we have sort of user expertise on the horizontal axis and technology sophistication on the vertical axis, it's kind of quite normal historically to view simulation solutions to be along an axis across this diagram. Through various kinds of customizations and engineering templates and so forth, we are very proud to be able to provide kind of much higher technology sophistication to maybe less experienced users by providing sort of packaged solutions or deploy established workflows which might be developed by the experts. At the same time, having the same tool across all degrees of expertise, it's very easy to scale the solution, starting typically with a simple, less complicated simulation, but as needed, we can gradually add more complexity and more fidelity to the simulation. It is a general package for structured simulation, and as an evidence of that, we can see that we have presence in almost all industries today. You can see a short list on the screen here, and this is because the generality of the simulation tools. Abaqus CE, which for most of our customers are the graphical front end. It's a modern, modular, well-organized system, quite similar to many CAD systems, I would say. It has a few years of history now, but for being an advanced simulation preprocessor, we were pretty early to be adopting a geometry-based approach rather than operating directly on nodes and elements, which many simulation preprocessors previously did. It offers modeling capability, but it's not the full-fledged CAD system. So for complex geometries, if you have the need for that, you probably have a CAD system anyway. So we focus on having strong interfaces to import the geometry and offer modification and repair and simplification tool sets in Abaqus CE. A next step for preparing a simulation model would be to create what we call a mesh, which is to subdivide the geometry into suitable elements or cells, if you will, which might require some simplification to ignore unimportant features, for example. skipping forward to the end of your simulation work, we normally produce a lot of simulation results, and for that purpose we have a very strong high performance visualization capability, which makes the user provides the user access to all the results we have computed. We offer transparency, view cuts, probing, XY plotting, synchronizations, animations and synchronized animations and so forth, and to be able to compare variants of the models. We use also Python for scripting and journaling. So with the Python scripting language, we can extend functionality. We can capture routine tasks, and we can extend functionality. We can also easily build new dialog boxes for providing an easy access to dedicated workflows. And we offer also a capability to completely customize the graphical user interface. So what we see on the left-hand side here is the kind of the out-of-box variant of Abaqus CAE, whereas on the right-hand side we see a full, what we refer to as a vertical application, which is a knee simulator, which embeds simulation methods, simulation technology, but also provides a customized front end for a user to provide the relevant input for creating and running that simulation. Turning our focus into our analysis products, we have robust and accurate nonlinear solver technology that can handle any model sizes. It's reliable, it's accurate. We have always been developing the code for the purpose of being for production use. So quality assurance has always been very important. The solver was initially born in 1978, and the last major rehaul of the architecture was in 2000, when we moved into new file architecture and new file systems and so forth. One of our more prestigious customers is BMW, as you can see, which the animation playing here, and they have really come a long way in terms of confidence in the simulation. So that means that they can largely, more or less, completely eliminate prototype hardware testing and have such confidence in the simulation results that they can dramatically reduce the number of very costly crash tests. For doing simulations of structured simulations like this, we kind of rely on the availability of material models, of course. And Abaqus offer a very comprehensive sort of library of material models for most of the materials used in industry today, like metals, rubbers, composites. We also have material models for soils, rocks, concrete, ceramics, pastes, and polymers. So the offering here is I would say, comprehensive. We also have a framework for damage and failure modeling that can offer bulk failure or delamination or cohesive modeling, if you will. Abaqus standard, what we call the implicit solver, is what most people refer to as a finite element solver. That is of course intended for static analysis, static stress analysis, and deformation analysis. But we can also do dynamic events. It could be vibrations, but it could also be transient dynamic events. Depending on the configuration of our simulation, it could be a linear or a non-linear behavior to be taken into account. You can see some examples on the screen right here. Of course, stress analysis, large deformation, clip incitation here, sealing simulations, tire noise, which would be typically a frequency domain analysis. Abaqus explicit, which complements the implicit solver, is designed for high-speed transient dynamic events, but can also be powerful for highly nonlinear quasi-static events, like certain manufacturing simulations. So we can see some examples for typical explicit analysis playing on the screen. Explosion and blast loading, of course, various crash types of simulation, drop events, fluid-filled bottle dropped to a rigid floor, for example, or some quasi-static rolling, for example, or sheet metal rolling could be modeled with this solver. Both of our solvers rely on powerful contact capabilities, which is accurate, but at the same time easy to set up. They require minimum of user actions. In addition to sort of relatively straightforward linear analysis, the strength of the solution is also that we can do much more advanced analysis. So one example could be like this turbo wheel, where we the turbine, we can see that we apply some operating condition, 10,000 RPM, and we can compute the eigenmodes for taking into account this centrifugal loading, and then this process could be repeated for various operating speeds, just to explore how the centrifugal forces will affect the stresses, and if we will see some resonances, for example. Other types of advanced analysis could be damage and fracture. What we see here is delamination of a composite structure for typically energy absorption capabilities. On the bottom left-hand side, we see progressive damage of fiber-reinforced composites. I think this is actually the understructure of the seat in a helicopter. So in the event of setting it down too abruptly, this failure mechanism will provide some energy absorption and spare the passenger or the pilot's backs. On the top right-hand side here, we see crack propagation, comparison with a test and the simulation. For system level simulation, we offer sort of something we call connector elements to offer a capability to a more simple representation of certain type of joints to improve performance of large system types of analysis. Multiphysics analysis are also part of the advanced setups, I would say. So thermal stress analysis, for example, where we can compute the thermal distribution, and the coupling to the mechanical field is oftentimes through expansion coefficient. We can do electromagnetic thermal co-simulation, for example, and map that onto to a structural simulation. We could do some fluid structure interaction type of simulations, mostly in the framework of Abaqus explicit, where we have something we call coupled Eulerian Lagrangian. So this is what we refer to as a Lagrangian method. So the fluid part here is modeled with stationary elements, and the fluid is moving inside the mesh. We also have particle methods that provides somewhat similar capability, but more powerful for other circumstances. We have recently developed some quite advanced capabilities for being able to include simulation of additive manufacturing processes. So that means that we can progressively activate the elements. So the element mesh will in this case be initially empty. So the elements will be there, but there will be no material in them, and then we gradually can progressively add material to the elements and automatically compute what are the free surfaces for thermal boundary condition, and independently prescribe how moving heat sources like laser, for example, that scans the geometry. That was a little bit about what Abaqus can do. On the SIMULIA platform, we also have some product called EyeSight. So this is our, let's say, software robot that can drive Abaqus, and it can drive multiple other softwares like Excel or other CAD softwares and so forth, and capture processes and passing data from one application to the other. And as such, it will also offer optimization, parametric optimization capabilities. So basically, without EyeSight, we typically see simulation work being a manual disjoint process, geometry, structural simulations, fluids, and so forth, which need manually to update the next step. Whereas with EyeSight, this could be captured and automated in a very nice way. We also have a product called Tosca, and this is also an optimization capability, but it's a non-parametric optimization. So this offers a way of doing what is known as topology optimization, which takes off sort of the material which experiences low stresses and recomputes, so we can minimize the weight and still meet the functional requirements. Sizing can change the panel thickness, effectively, of shell structure for the same purpose of reducing the mass, but to meet certain functional requirements. Shape optimization, that's the fine tuning that will change the radius, for example, at certain fillets to reduce stresses, to increase durability, performance. The bead capability, optimization capability, can introduce beads to change or modify the eigenfrequencies to avoid undesired frequencies. Similar to the topology structures, topology optimization, there's a somewhat similar capability for fluids that can optimize the shape of the fluid domain to reduce pressure drops and so forth. FE-Safe will be able to read and use the results from our simulation data and process that into fatigue life. And there is a wide, very comprehensive offering of various fatigue algorithms, both in the time domain and in the frequency domain, to complete the durability assessment. These results will then be written back to the same results database, so you can use the same tool to visualize the fatigue results. So that was a little bit about the products we offer for structural simulations here. So with that, I'm going to talk about some examples and example trends and some examples where we that hopefully will help you to understand how you can use simulation to predict and explore the product behavior under the operating conditions that your product will see. So just to start with, I'm going to talk a little bit about pump assembly. So this would represent something which could be a pump, of course, but it could be the same for any object in process industry or even nuclear industry or anything like that. So this, we're looking at this outer structural parts here. So there is a housing, there's a cover, there are some bolts. There is a particular gasket coming in here as well, and the loading we are considering for this case is primarily the bolt loading, and then there is an internal pressure that we're going to look at here. So first, a few words on bolt loading here. So you can see that there are a number of bolts attaching the cover here to the pump house, or to the cover or the bottom piece here. Bolt modeling might sound as a trivial thing, but it's really not in terms of simulation. So what we have here is a capability to use various abstractions of bolts, of course, but in this case we have made a full 3D representation of the bolts. And the loading consists of two parts. So first we apply a force. That would be an axial force on the shank of the shaft of the bolt. That is the first simulation step. And then, of course, the bolt contacts, there's a contact definition defined here, so it's contact between the pump house and the bolt head. And then the pump house contacts the gasket, and the gasket contacts the bottom cover here. So there is a lot of contact going on here. And the first step then is to apply the torque or the force on the bolt. And then at the end of that step, as a result of this loading, there will be a change in the length of the bolt, right? So at the end of that step, we fix the length of this bolt. So you can see the analogy here. In reality, you would actually turn the nut here. And we will probably measure the torque and not necessarily the axial force. But the number of revolutions that we turn the nut here, that will represent a change in length, effectively, of the shaft of the bolt. So for subsequent loading, the length of the bolt will have to be fixed, and any additional loading will have to be accommodated by further straining the bolt. So the load scenario then is tightening the bolts, fixing the length of them, and then in this case we apply an internal pressure inside the pump housing here. So this is just a stress plot of the assembly after the bolts are being tightened. So we can see, of course, that there are some higher stresses around the contact areas, the edges around contact, which is kind of natural and intuitive. What I wanted to talk a little bit in more in depth about here is what would be the functional requirements of this kind of structure. Well, of course, it shouldn't sort of fail at the point of tightening the bolts, but we obviously would like to make sure that under operating conditions that there is no leakage. So what we see here is I isolated the gasket part here. And what we see here is the contact pressure at the point where the bolts are just tightened. Obviously, for durability, we probably like the pressure here to be quite smooth. We really want to avoid having very nasty stress concentrations and so forth, because that usually will mean that there's a risk of wear and tear and ultimately failure of the gasket at that point. If we switch to the next slide, we will see what is the contact pressure at the point of operating condition when we have an elevated internal pressure in the pump house. So if you go back and forth here, we see that it kind of looks, different. I would say that for as an initial sort of assessment, in order to make sure that there is no leakage, we would like to make sure that the contact pressure here is sufficiently by some margin higher than the operating the internal pressure that we're seeing in the pump. And this is an example where simulation really can be much more efficient than experiments in order to explore these kind of conditions. For more advanced, in this case, we only are looking at kind of the contact pressure as such. We have capabilities to include also pressure penetration load, so we can see what happens if the contact pressure comes down to zero at some spot around the interior here. And what will happen if the interior pressure would actually be penetrating in between the surfaces and subject the contact surfaces also to internal pressure, and see if that will lead to additional deformation and additional risk of leakage. And of course, now we could kind of unload, remove the load, and see if there are any permanent deformations of the gasket, for example, and reapply the load and cycle the loading to see the stress range, for example, for fatigue assessment. So this was an example which I think a lot of us can relate to, where simulation can be really superior to experimental efforts to validate the product performance. Other aspects we could take into account are, for example, manufacturing tolerances. So we could include some kind of initial deformation of the pump housing, for example, tolerances of how flat the surfaces are, and so forth. That will obviously affect the contact stresses. Other aspects could, of course, be changing the torque, the loading on different. Now we have the same one on all bolts. Potentially, we could have different torque on different bolts, if you will. The other thing I wanted to demonstrate a little bit has to do with topology optimization. I mentioned the Tosca capability that we have, and basically we're just to demonstrate that this is a pedal assembly for a car, and we take the brake pedal here for demonstrating that, and we can see that we have a CAD geometry here, which looks as if it would be a relatively big component. But in this context, this is defined as the design space. So the design space is sort of location where it is allowed to have material, but the solver is allowed to remove material as required to make it as light as possible, but at the same time meeting some of the design constraints, which could be the amount of flex and deformation and so forth from the loading on the pedal here. So what we see here as an animation is the how the solver, various iterations, that is various attempts for finding a solution, and so we can see as it gradually removes material. Sometimes it removes a little bit too much, and then we have to go back a little bit. So this would be a light design that would meet our functional requirements in terms of flexibility and strength, and at the same time reduce the amount of material that we need for producing it. Another trend we see in the simulation community is that the fidelity of the simulations are such that it's becoming more and more relevant to include the manufacturing history of the parts. So that could be additive manufacturing, it could be casting, it could be forming. All of these operations will effectively produce residual stresses and so forth to the material, and which is already present when the part is produced, and might have some effect on how we evaluate the result of the product performance. Composites is also another topic which has been quite intense in terms of development for some time, particularly within aerospace industry. So for that type of simulation, we will have an add-on called Composites Modeler for Abaqus that can take into account the draping aspect of how we produce composites. So basically, we can start with a flat pattern and we can drape that onto, by a projection method, onto the actual geometry. And as a result of that, we can get the fiber orientations and so forth on the actual geometry, which will be required for accurately computing the product performance at a later point. I mentioned additive manufacturing previously, and this is of course as well to be able to compute the manufacturing, to simulate the manufacturing process, to predict the distortions, but also the how we can compensate the shape before producing it, so that the end target will match the nominal geometry, but also to be able to capture residual stresses and so forth, and basically drive the manufacturing process to improve the final product performance here. So these simulation capabilities developed for additive manufacturing will really be useful for addressing kind of long existing production processes like welding and so forth. So welding is really, if you look on it, it's really a kind of an AM process, because we add material and we add heat, and this capability can quite easily be used to include that in the history and come up with the distortion and residual stresses that will be the result of this process. So basically, what we have here is a set of analysis products developed for providing realistic simulation for all industries and all users, including linear and non-linear behavior. We can deal with very advanced and sophisticated contact and materials. High performance solvers will offer for short turnaround times. We have a modern and easy to use graphical interface that integrates well with the popular CAD packages to make a streamlined way of creating the models, which it also offers a strong customization capability for deploying workflows to advanced workflows to maybe less experienced users. So it's really a single solution for all needs. Okay, that was what I meant to talk about. So Friday afternoon and so forth. So any questions or comments?
Yeah, thank you, Jan, for a great presentation. That was very enlightening. There are actually some questions if you do have a couple of minutes before we go out for weekend, I guess.
Yeah.
So can material test data be automatically calibrated?
Yeah, that's an interesting thing. Yes, we have Abaqus has offers a library of material models, but not necessarily, the data to populate all the parameters here. We are constantly working on calibration methods. So in Abaqus CAE, we offer a tool that can partially, sort of, for some material models like hyperelastic rubber type of materials, viscoelastic materials, elastoplastic materials like metals and so forth, you can just import your test data, and you can have the solver and the preprocessor to come up with the best fit to your data. Not for all the material models, but for some of the most used.
Okay, great. Yeah, thanks. So next question is, can you do fatigue crack propagation analysis?
Yes, there are multiple sort of ways of dealing with that. But combining it with the what we call the XFEM, the extended finite element method, we can initiate and we can grow a crack, and crack growth analysis can there's a special procedure for that. We call it direct cyclic, which basically, if you have like Paris law type of coefficients, we can predict the crack growth as a function of the number of load cycles. Yeah.
Okay, great. Yeah. So the next question is, what CAD formats can be imported?
Most we have this, of course, native CAD import from CATIA, SolidWorks. We can also take the import step files, IGES files, of course, and we can import. Yeah, that was good. Yeah, I think we can do, I would say, most of the CAD files, but I think generally the unless you have the direct sort of if you have CATIA or you have SolidWorks, we can do ProE files. We can do. I think that's pretty much what we have. But I strongly recommend, sort of, if you don't find it directly, the direct interface, we can. The step file format is usually the most powerful one. But let me check my list here. So yeah, I just step V5 Parasolid, VDA, ACES, as I mentioned, that's the native format of Abaqus CAE. And the SolidWorks files. Yeah.
Okay, good. Last one before we stop here is, can wear of material due to friction/slipping be modeled?
Yeah, that's it's part of one of the more advanced work. But yes, we have a user subroutine interface to offer the capability of modeling wear of parts. So basically, you will have to write an extension to the code using typically Fortran. There are lots of subroutines available for Abaqus for extending the capability, but this particular one will have access to state variables, conditions in the contact surface, like contact pressure, slipping, the amount of slipping, temperatures, and so forth. And based on those conditions, the user can specify a rate of wear that will be passed back to the finite element model. And that means that we are slightly moving the nodes in the contact surface. And at the same time, the solver will remesh or adjust the elements on those parts to avoid that we are actually completely removing the elements. So with that, we can model wear, or basically if the user specifies kind of a negative wear rate, we actually are growing material, adding material on the surface. So it's up to your imagination to figure out what that might be. I've seen people using that for taking into account corrosion, for example, in some circumstances.